Hello guys. So I'm a new PhD student at IDSL group at Western University. Today I'm broadly interested in computer vision. Today I will be talking about neural radiance field, uh, which came out in 2020 to address the problem of novel view synthesis, which is a graphics problem mainly, but since then it has been used quite heavily in other vision problems as well. Uh, so, but this has this was kind of a revolution when it came out, but then within 3 years this was largely replaced by another technology called Gaussian splatting, which I will try to present sometime later. Uh, so. Uh, so first, these are the topics that I will talk about today. Uh, I will start with some basics because I assume some of the audience might not have might need some background in graphics or view representation. So I'll start with 3D shape representations, and I will talk about the problem of novel view synthesis, and then we will discuss the core of NeRF, which is Neural Radiance Fields. And then fourth, we will look at how do we do rendering with radiance fields. And then finally, we will see training the NeRF framework. I'll just quickly show their project page. Where they have these cool demos. So you can see, if you see this video here, this is not a video actually. This is a rendering from NeRF where they have captured multiple images of this scene and trained the NeRF model, and now they are able to move and look at it from different angles. So this is the problem of novel view synthesis. We will look at it more rigorously in our presentation. So this is just to give you motivation of what kind of work that this. So before NeRF came out, then the quality of this novel view synthesis rendering was nowhere as close as this. So there was a huge jump in the quality once this paper came out. So that's why it is still relevant to look at what ideas were used in this paper. So first, we will look at 3D shape representations. So there are many ways to represent 3D shapes. I will just briefly talk about 4 of them. The first one is mesh. In old games, you must have seen these vehicles and people being represented by triangles. So that kind of approach is mesh. We will discuss each one of them in detail. The next one is voxel grid. And the third one is neural network based 3D representation, which is used by NeRF. And the fourth one is 3D Gaussians, which is the state of the art at the moment. First, mesh. So in mesh representation, objects are constructed from geometric primitives. So usually triangles. So if you look at the rabbit on the right, like they have created a 3D shape of rabbit using just triangles. This is classical approach. You may recognize this kind of visuals from old games. So this represents only surfaces. So in this representation, we only care about the surface. We don't know what's inside. We don't care about what's outside. It's just the surface of the 3D object. And this can be once you have this mesh representation, you can do some ray tracing and rendering. We will discuss this ray tracing in detail when we talk about NeRF rendering. So it also uses this ray tracing and rendering. So this is mesh. Then the next one, if you have any questions, just feel free to interrupt because we only have 4 people today. So I don't mind interruption. So you can interrupt and ask questions if you feel you don't understand anything. Then the next is voxel grid. So you know pixels. So in image, let's say if the image is 1024 by 768, then you have that many pixels, which are like dots in a 2D grid, which represents RGB values. You can take the similar idea to another dimension by adding a 3D dimension. Let's say you take 1024 by 1024 by 1024 cube, and then there are these small cubes inside, like you have 1024 to the power of 3 small cubes inside that big cube. So you that each small cube is considered as a voxel, which is a 3D pixel. Voxel is just a 3D pixel. So you can give RGB values to this voxel, and that can be taken as a form of representation of 3D space. So objects represented as scalar values in a 3D grid. So yeah, there's a can represent volumetric information. So previously in meshes, we saw like mesh only represents the surface. You don't you don't know what's inside, or you don't know what's out, if there is any other like light object. If the rabbit has some fur, like the mesh, it's very difficult to represent that. But in voxel grid, like you can like put voxel, like you can color voxel grids inside the object and keep some volumetric information. So that's what they're saying, can represent volumetric information. Rendered via several methods: ray matching, alpha compositing. So this we will discuss later. Just know the terms now. We will discuss this alpha compositing later. And then one challenge is that finer details require higher resolution. So we saw that like we take voxel, like small grids. So if you take like, I think this is a lizard at the bottom. So from left to right, the resolution increases. So we make the size of the 3D cubes, like voxels, smaller and smaller as we go to the right. So on the left, if you see, it uses 902 voxels, but the image is a bit blurry, like you don't get the finer details. But if you go to the rightmost one, there are 71,000 plus voxels. You see the finer details. But then like if you try to represent a big scene in this manner, then you might need a lot of space to store all these 3D information. So it expands cubically. So if it's like 1024 to the power 3 cube, then if you want like there's a cubic factor, the exponential increase in the number of storage space that you need. Then we will talk about neural net embedding of 3D space. So if you look at this 3D shape representations, some of them are explicit, some of them are implicit 3D representation. That means like uh, finally we have to, like you have a 3D representation, then you do some rendering, then you come to the 2D image. But some of these representation, even without the rendering component, you have some notion of 3D shape or image. So those are called explicit representation. So if you take a mesh or a voxel grid, like even without doing like, anyway these are rendered images, but even like in your head you can imagine that if there is a mesh like this, like even without doing any rendering, like there is a notion of shape, there's a notion of like surface and stuff. So these are called explicit representations. But the neural net embedding is an implicit 3D representation, because like you use a neural network to store a 3D scene, but unless you go through the rendering process, you cannot look at the neural network and see, oh, this is a 3D representation of a rabbit, this is a 3D representation of a lizard, and so on. Like the information is implicitly stored inside the neural network. So unless you do rendering, you don't know what is stored inside. So these are called implicit. So just some classification between the methods. So uh, any questions up to this point?
Just a little one question, right?
Hmm.
So in the meshes part, you are
Hmm.
actually you're creating the meshes, but Even to represent these meshes, you would need like I'm thinking in terms of storage capacity, you would still need to build some form of angles and what is connected to what, and that would also blow up your memory, right?
Yes. Yes, true. I'm not a like a rendering expert, like I'm not a graphic expert, but here also like having this. Let's if you look at this region between the legs, that like it has finer details. It requires a lot more triangles. So as you correctly mentioned, like this would also blow up. But since we only represent, like my idea is that since we only represent surface, it will be a quadratic increase in the number of like parameters or storage required. Whereas in voxel grid, like you represent the entire volumetric space. So if you try to increase the resolution, it'll be a cubic increase. But in meshes, it will be a quadratic increase. That's my thought off the top of my head.
Mm-hmm. Uh, why? Wait. So cubic increase, wouldn't it be to the power 4? Because there is height, width, and then you have RGB. Like the third dimension is RGB, the color space, and the fourth dimension is depth. So wouldn't that be power 4 increase?
We only talking about when we increase the resolution. That means like we when we increase the spatial resolution, like
Uh-huh.
whether
Okay.
that is
That's it.
proportional to a cubic increase in
That's
the
cubic.
number of voxels. But as you rightly pointed out, each voxel will have RGB, so that cubic increase will apply to like at the end of the day, we want to store RGB values per voxel grid. Then the cubic increase will actually apply to that RGB storage numbers. Like if there are 902 voxels, there will be 902 RGB values that we have to store. And it not only RGB, there could be some other, like there are these light transport properties that we have to capture. So as we will see in NeRF, there are some other parameters like RGB that we need to capture per point so that like we can do good rendering. So yeah, so once you increase the spatial resolution, the number of voxels will blow up in cubic, and then
Mm-hmm.
per voxel, like the RGBs that you will need to find the storage space. Yeah,
Mm-hmm. Yeah. Yeah.
interesting,
Okay.
interesting questions. Thank you. So uh, we'll look at there are several neural network based embeddings that people have tried. So uh, like the so here in this 3D representation or novel view synthesis, like first we do a 3D representation, then we go to novel view synthesis. I will talk about what novel view synthesis as well in a moment. Uh, so typically how we use neural networks is that we have, let's say for classification, we have images of dogs, images of cats, and then we train the neural network to do some classification. Do like it tries to learn from the images and try to learn some feature vectors where we can separate these two classes. So that's how we typically use. But here for this 3D representation, it is used in a very dumb way. Like it doesn't learn any latent space representation or like any semantic information about whether this is a cat or a dog. What how people have used neural networks in this area is just use a neural network to memorize a single scene. Let's say you have a scene of a rabbit. You just take a neural network, just overfit to the network to just this one scene. So it memorizes this entire scene so that you can query from multiple angles and get how yeah, the rabbit looks like from different angles. So that's kind of like the basic idea. So there are different ways, like you can train a neural network to give signed distance. So you give a point in space, and you can query the neural network to give what is the distance from that point to the surface of the object. So if you go back to the rabbit, so if you take a point here, if you train neural network with that signed distance metric, then it will give the perpendicular distance between that point in space and the point on the surface that has right angles. So that is one way of training neural network to represent 3D space. So then, like for each of these, the rendering technique will vary because you get information in several modes. Then you have to render it in different ways. This is just one idea that people have tried, which is sign distance. Then the other is occupancy field. Occupancy field is like, let's say you take a point here that is in empty space. So the occupancy field will say, okay, no, nothing is here. If you take a point inside the rabbit and query the neural network, then it is actually occupied by that object. So it will give some information. Yes, this point is occupied. So that is the basic idea of Like these are not directly relevant to NeRF, but we are just looking at what people have done in the past, so we get a good idea about how and why this idea of NeRF came into being. So that is one. Then the other aspect is you like these are like you give a point in space and you go to sign distance. This function, there is a function in the middle. So neural networks are used to approximate this function per scene. For each scene, you will have train a neural network. Then the other idea is, third idea is you go from XYZ to feature vector. So this is the closest idea of this is the closest classification of NeRF. So you have a point in space and you go to a feature vector, and this feature vector can be like people have tried different things to this. So the feature vector can be RGB color. So each point in space, what is the color here, what is the color here, what is the color here, what is the color here. So you can just give a point and query the neural network, what is the color there. That's kind of like a NeRF's approach, but then there are additional stuffs as well that we'll discuss. And then there are other approaches as well, like you use LSTM to predict march distance. So you take a point in space and then you can query the neural network how far along you had to travel to get like meaningful information from the scene, like where you had to terminate your like the lookup so that you get information. So I'm also not very clear on, like I haven't studied these apart. So these are like, I have brief ideas about how people use these. So yeah, so finally we have this idea about where the input will be some point in space, and then you get RGB plus some other information. This is the kind of approach that NeRF is taking. And do you have any questions until, like, this is just brief overview. I'll just go into the details in the other slides. Okay. Okay. If others also have any questions, feel free to ask. So, one thing is that this NeRF neural network based storing of 3D representations require large training time. Like we need to spend a lot of time training the neural network to overfit and memorize that scene. But then the storage is low. So the neural network learns to store this 3D information in a very compact manner. So here we see so that like to get a fine representation, we need to use like large number of voxels, and the number of voxels blow up in cubic manner. So to get really fine details, the storage cost will be very high. But when you use neural net embedding, like even to get very fine details, the number of neural network parameters that the network has to store is low compared to getting the same resolution with voxel grid. But of course, it requires a large training time. That's the trade-off that people have to make here. And also, this is a continuous representation. What do I mean by continuous representation is, so here there's a limit. So if there are two voxels, let's take this voxel and this voxel. So there is nothing in between. This is light green, this is dark green. So even if you try to query, like let's say you query one point here, you query one point here next to each other, but if they fall within the same voxel, then there is no difference, like they get the same information. So, but there is a discontinuity here, and then you start getting other values here. So this will be like, if you look at it in a 1D manner, it will be like this, some kind of like, just to give you an idea, it'll not have this continuous. But if you take neural network, let this be some dimension in space X. So if you take neural network, you can have this smooth approximation where you can give the X in different steps, and you can get different values from the neural network output. So that is what they mean by continuous representation. So there is potential for higher resolution. Okay, so yeah, so then now we will look at, like, so far we have seen several ways of, I have discussed the first three. I didn't discuss this 3D Gaussian because hopefully I will be able to do a big, like a presentation just exclusively on 3D Gaussian. So these are ways of represent. So this, and these three are explicit representation, and this one neural network is implicit because of the reasons that we saw before. And now we will go into novel view synthesis, which is like image classification, image captioning. This is also like a graphics or a computer vision task. Uh, so we'll look at what it is. This is computer vision task of generating new photorealistic images of a scene or object from viewpoints not present in the original input photos, effectively creating a 3D understanding from 2D data. So what they mean is, let's say you have a tree, and you take photos from different angles, okay, and you take all this information and you train some system, and then after training you should be able to generate an image where we will be able to look at how the tree would look like it at an angle that we have not captured in our training images. So that is what is. So this is novel view. Novel is like new, and this is a novel view, and these are like views that are present in the training data set. And then this novel view we have to somehow synthesize from this representation that we are learning. So that is why they call this novel view synthesis. Any questions from this? Okay, so there are different approaches to solve this. So there is traditional geometry, we saw that mesh, and then volumetric discrete. So voxels are volumetric approach, but then discrete. And also there is another approach called interpolation of light fields. I will just briefly show you. Like, these are just other approaches which are not directly related to NeRF, but it helps to know them. So just some, I am also not an expert here, so I have a very superficial understanding of these topics. So, and then volumetric but continuous. So NeRF has this volumetric continuous representation. So we will look at them. So first one is traditional geometry. The task is convert set of 2D images to mesh. So in traditional geometry based approaches, what we do is we take, let's say, 5 images of, not five, like we need a lot of, like, hundreds of images to actually do a 3D mesh reconstruction. So you take different photos of the same rabbit in the same pose, and then try to create this mesh. That is the uh, traditional convert set of 2D images to mesh. Approach gradient descent using ground truth minus rendered image as loss. So what you can do is you can take a mesh to represent some scene, then you render it from a not like a, let's say you have a tree, then you have photos from these angles. Then what you do is you create a mesh of the tree and then try to render it from the same angle as one of the images in your data set, then you have this ground truth image here and you have this rendered image here. You can do some comparison between these two images and calculate some notion of loss and then do gradient descent and try to train this mesh. Any questions on this idea? Okay, so this is an interesting limitation. This has this topological implications. Uh, uh, so the limitation is that we require an initial mesh with fixed topology. So anyone who wants to comment on this limitation, why this is why this limitation is a hard problem?
Yeah, I don't understand what's meant by fixed topology, but yeah, requires initial mesh is like that's a very big limitation that you need to have that ground truth
Yeah,
of
yeah. So
reconstruction.
yeah, so yeah, okay. So like topology is like a huge field in like in mathematics. And if you are interested, like I think there are these fundamental conjectures. Like I think point, yeah, you can read up about this. So this is a million. Like there are like a lot of like there are conjectures that have been framed as this millennium prize problem, like
Mhm.
maybe 10 problems they have formulated, and each problem has a, if you solve it,
Mhm.
you basically get $1 million. And this is the only problem that has been solved. This is in geometric topology. And like that, like these are kind of like frontier areas in that mathematics field, but you can just read up about it if you want. The scientist who solved it basically said, "I don't want the $1 million." So
Yeah,
that's
yeah, I read about that. I read
okay.
about
Okay,
that.
so let's. So if you take a don, oops. So what topology says is that like if you take a donut, okay, you take a donut and then you take a cup, okay, you take a ceramic cup with a handle. So these two are topologically same because there are ways to continuously deform this 3D shape into this and back. You can imagine as you take this ceramic cup and then there is a hole here, okay, there is a hole here and there is a hole here. So what you can do is you can take this and massage this cup, like you can just, this is just a cup with like you can imagine there's a hole in the middle, right? But what you can do is you can just compress this cup from top and bottom, just flatten it and make it like a ball, and then you can then massage this handle into that, and then you can just reduce the volume on this side to just bring it to this space. Do you get the idea?
Mhm.
You just massage the cup, like you just think of cup as like made out of clay, and then
Yeah.
without breaking the clay or poking hole into the clay, you can change this into this and back forth, because these are topologically identical, because these are just some spherical object with the hole in the middle. So if you just massage this into this part of the this and then add some so you can just reduce the size of the hole here, then it becomes this.
Mhm.
But then
Yeah.
if you take a spherical ball, then donut and ball are not topologically identical, because you can never, without poking a hole or like breaking it apart, you can never massage this into a spherical ball. But if you have a clay, you can just push and close the hole, but that is not the operation that we are allowed to do. So do you get the idea that what they mean by topologically identical to the object? So if you are trying to, let's
Mhm.
say you are trying to, you have a cup, okay? you have a cup and you are trying, this is the 3D object that you want to train. If you start with a mesh that looks like uh, a donut, you can do this gradient-based optimization to train it into this cup. But then
Yeah.
if you start with the mesh that is like a ball, you cannot do gradient-based training to, because this will be a discontinuity in that gradient flow. So those are like some high-level idea, but I think we don't need to go into that detail here. That is what so this is the limitation here. It requires a mesh with fixed topology. So do you get the idea behind this?
Okay. So,
So we need to know, like, so if we are training if you are training 3D representation of a cup, you need to know that you have to start with this donut. If you want to train a scene with a vase, let's say there's a vase that, like, vases have two handles, right?
yeah.
So for this, like, you have to start with some kind of a mesh that has two holes. So you need to know the starting mesh. So that is a hard problem with, like, gear. So you cannot knowing the starting mesh is a difficult problem. That's what they mean by requires initial mesh with fixed topology. Because during the training, what we do is we do gradient descent. Gradient descent, we can change the shape, but we cannot break the actual topology.
But why is that? Like, why can't you break the topology while you're training a new? Why does it only morph your space, not, you know, do something like this?
Yeah, like, I'm also not very clear, like, how what imposes that limitation. As I mentioned, I'm not, like, this is my idea. So, like,
Oh, okay,
like,
okay, okay. I
imagine
got it.
there
I
are
got it.
lines here. There are a lot of lines here. What you
No,
can do is you can move this in 3D space with like, you can move this in 3D space with
Mhm.
gradient adjustments. But then, like, let's say there is a space here. There's a, let's just not imagine 3D, but just imagine 1D. There's a line here, but then with some gradient adjustment, you can make this line into like this. But then you cannot make this line into something like this. So yeah, that will be a point of singularity. So, like, you cannot break it. So with gradient based adjustments. So that is my idea.
Yeah, that's what I was also thinking. So each layer in a neural network is like a non-linear transformation, right? So it's just morphing the space. It's not actually breaking it apart and doing something
Mhm.
like that. So you are actually morphing the space, not you cannot break it apart and do something weird with it.
Yeah, yeah. So that is my idea. So that is the limitation here. I think.
Yeah,
Uh,
just one quick question.
yeah,
Like,
yeah, yeah.
what is
Go.
the formal definition of like topological identical things? Like, how is it?
Uh,
Like in your words, it is like this, right? You are explaining.
I will have to, like, search and give you an answer. So
Mm.
I am not a, like, a math topology expert. I have some very, surface level ideas, but
Mm. Got
rigorous
the idea. Yeah, I got the idea.
rigorous definition, like, maybe you can search, or I will search and I can let you know later,
Mm.
because that I don't know, like a rigorous definition why this donut and cup are the same, but then donut and football is not the same. Like, rigorous definition I don't know, but then this is the verbal understanding that I have. So yeah,
Mm.
thanks for bringing it up, but, like, for the moment I have no idea about rigorous definition.
No problem. Yeah, go ahead. Thank you.
Yeah. All right. So, so the next idea is volumetric but discrete. So you can take a set of 2D images and train a voxel grid, a 3D voxel grid. So uh, classically, what people do is they take a 3D grid and try to, do a lot of linear algebra. They take views and then camera's intrinsic and extrinsic parameters. So you draw a lot of lines and then you take the intersection between multiple views and try to pinpoint what color is there. So a lot of algebraical stuff people try to do in the past, but then after this neural networks, CNNs came into being, people started using CNNs to encode and decode voxel grids. So what you can do is you can take a lot of images and then you can use an encoder to predict some latent space vector, which can be taken as a representation of voxel grids. So I don't know how they actually do it, but this is one idea that people have tried. So I don't actually know how latent space is related to the 3D voxel grid space, but people have, oops, bad drawing. Okay, yeah. People have used this encoder decoder kind of idea to construct 3D voxel grids. Then like even if you take classic approach or the novel CNN based approach, they are still limited by the voxel grid resolution. So you have a voxel grid which you try to train, like which you try to fill using either classical approach or this encoder decoder solution. So anyway, and at the end of the day, they are both limited by the resolution of the initial voxel grid that you are choosing. And then the other idea is interpolate nearby images. This is, I think, interpolation of light fields. So I'll just be a little bit more quick because like we haven't even reached, like we are just still in the introduction, like we haven't even reached NeRF. So we haven't even gone to the presentation that I wanted to do. So yeah, so interpolation of nearby images, what they do is they take a input image, then they convert it into a multi-plane image. So they like partition the image into multiple planes based on depth. So this flower is in the foreground and this is in the background. And if you look at it from here and here, the foreground will move with respect to the background. So people have tried to predict this kind of movement so that like you can get some notion of like you have two views like this, then you can have something in the middle or something just outside of what you have. But then I would imagine that this you cannot go and query from somewhere outside the training range because this is not it doesn't have a very good 3D representation. So it may like this is just an interpolation of nearby things. So it might work close to the training pixels, but not outside of training images. So okay, so the next one, okay, novel view synthesis. The next one is volumetric and continuous. So this is where NeRF falls into. There are a lot of approaches into this, but then NeRF is also one other approach here. So task render from some continuous representation of space. You should have a continuous representation of space. That means like x is equal to 1, x is equal to 2, x is equal to 1.1, x is equal to 1.115. Each point in space will have some RGB or some value in the output. So that is continuous. You have a continuous representation, and then you try to render from there. Then the prosa, these are not limited by discrete nature of voxel grids. Of course, it's not, and can be trained from sparse input set. So I think I don't know why this is, but then I think empirically they have taken sparse set of input images, but able to train a good continuous 3D representation model. And the con is previous approaches only demonstrated smooth, low frequency features. So before NeRF, I think using neural network with sign distance or some other tech approach, they were only able to do smooth objects like let's say some ball or some smooth object, but then not objects that have very rough texture or very abrupt changes in its appearance. So that was a con. Then
Yeah,
came,
for
sorry.
the second point can be trained from a sparse input set. I think that means that the images that you're training on, they are actually discrete, right? They are not continuous.
Yes,
So that's why they're saying a sparse input set, because you don't have values between two pixels.
yes,
It's
correct.
limited by the resolution, but you're
Yes,
actually predicting in the continuous space.
yes, yes, yes. That's
Mhm.
one good way to look at it. Yes.
Yeah.
I would also like to think, let's say you have a, tree here, and like if you want to do this interpolation of nearby images from any angle, then you need to have a lot of images that looks at this tree from all, like, I don't know, maybe 10,000 possible view angle, so that like
Mm,
even if you pick something here or something here, you have some nearby ones, so you can interpolate. But then this volumetric continuous thing, like you have a tree, and then you can take, let's say, I don't know, 100 images, and then you will be able to do continuous. Uh,
yeah. Yeah.
yeah,
Yeah,
so
right.
some notion of sparsity, as you mentioned in the, like, we don't have continuous information in the 2D image, but then in 3D we have continuous information. So now we go into the objective of NeRF. It's 11:20. At what time do you want me to stop, Arath?
No, you can just keep on going.
Okay,
Yeah,
okay.
yeah.
Yeah. Okay, so the objective of NeRF is, given a set of input images, optimize a continuous volumetric representation of space of a scene. So you have a input is a set of images. Then the train in the training procedure, the input is a set of images. Then the output is some no, some neural network based continuous volumetric representation of the scene. So, fitting a multi-layer perceptron to implicitly represent just one 3D scene. As we have seen, we are not learning anything semantic. Like after training nerve, the network doesn't know whether, like here, this image is from the paper, and they are training a scene with this drum set. The network, even after you train it, it doesn't know this is a representation of a drum set. It has no idea. It's a dumb network that has no idea about the semantics, but then it does a very good job of memorizing this 3D scene, so that you can query from any angle and get the thing. So see, in the input images, they have a lot of images of the drum set. Then if you like these pyramids are camera, like they have taken these images from multiple angles. So these pyramids are representing those camera views from which the input images are taken. So you have information from, I don't know, like a, semi sphere. Then you train a network. Then you get a continuous representation where you can just like in this, you have seen they are moving doing a continuous movement. So you get in every place you get you, for this they may have, like they didn't take a video, right? So as Arath mentioned, they don't have information for every viewpoint, but then after training it is able to generate uh, outputs for every point. So now we go to like some rigorous definitions. So NeRF models a continuous 5D radiance field. So the long form of NeRF is neural radiance fields, and the concept of radiance field existed long before it came out in the 90s in physics, and it existed for a long time. The NeRF is just a neural network based representation of radiance field. So you can imagine a radiance field as, let's say you have a radiance field here, and you have each point in this radiance field will emit some light. You can, like, some RGB color, each point will emit some light. You can think, like, if you take a TV, each pixel is emitting some light, right? So your eye is seeing all the combination of all the lights from all the pixels. So imagine that in 3D. So there are points, each point will emit some sort of RGB color. Okay. So there are several ways of quantifying a radiance field, like what are the inputs, what are the outputs. So I think it's a 7D field in the, like in literature, radiance field, but in NeRF they have chosen a 5D radiance field where 3 dimensions are used for position, like the location of the point in space, and two angles are two 3D angles are used to represent viewing space. So so the input for NeRF is not just the 3D point, but also from which angle we are looking at it. So to represent angle in a 3D space, you need 2 angles. So for viewing direction, you have 2 dimensions, and then 3D positions, you have 3 dimensions, altogether 5 dimensions. So that is the input. So any questions on that?
So the 3D position represents your viewing position, right?
No,
From where you are
3D
viewing.
position is the position of the point in space that we are interested in. Let's say we are interested in this point in the 3D space.
Mhm.
This angle is about from what angle we are looking at that point. Are we, like you can, if you fix this XYZ, and if you change this, one way to look at it would be like this. Another way to look at it would be like this. So this has
Okay.
different angles. So another way to look at it would be like this. So this has a different angle. So these three are 1, 2, and 3. These three are where you keep the XYZ constant and you change this angle. And also, I would like to give you an example of where we keep the angle constant, and if you change XYZ, if you fix this angle and you change XYZ, this is one XYZ, this can be another XYZ, this can be another XYZ.
Mhm.
So
Okay.
you are viewing at it from the same angle, but then different 3D points.
Okay. So the 3D position is for any point in the space.
Any point in the space, and the angle is from what angle we are looking at it. And we will come to a place where we actually see why this viewing direction is needed. And I think the conversation is our discussion is going into like a very detailed physical aspect rather than the neural network based NeRF approach. But then I appreciate that, because like these are fundamental things that we need to understand, so that we get a complete picture of what's happening. Not just, you take these images, you take this neural network, bang, you get so I like these discussions, but the thing is that it will take a long time to get through this. So yeah,
Yeah.
so these are, if you fix XYZ and change angles, you get these different views. If you fix the angle and you change XYZ, you get different things. But also, this is with respect to a fixed origin, O1. If you take O2, then you can have the same angle as this, and but different XYZ along this line. Do you get it?
Mhm.
So if you move the origin, also it's so when we start with rendering, we actually pick an origin where we want to place the camera, then we do the rendering. Okay, so these are the inputs, and the output is that for each point, we get a volume density. So let's imagine, if you take this as a cloud, let's imagine this as a cloud, and this part of the cloud is like very dark, dense. That means like a lot of gases are there, and it is dense. So any point in this part will have high density. And let's imagine this part of the cloud is very light. So the density would be low here. That, like, we will also look at why this density is needed to do rendering. So as output, for each point and viewing direction, the network will give volume density sigma x all greater than or equal to 0, and then view dependent color C. So for each point, we will get RGB values, which is a vector. So C is equal to RGB. And then like from the notations, you can see the density depends on the location in space, but the RGB values depends on the location on space, also the viewing angle. So if you take this point and you query from this rendering, let's think of this as 3 different renderings, and then for each rendering, this particular point will give the same sigma value, but then it will give different RGB values. For this rendering, this point will have different RGB. This rendering, this point will have different RGB. This point will have different RGB. So I will come to that point later also, like in a couple of slides. So there we can discuss that in detail. Just I'm introducing inputs and outputs. So these are the inputs: 3D position, viewing direction, and the output is density and view dependent color. So the neural field that we are interested in is a function f theta parameterized by theta, which is a function of x comma d 3D position, and this x is not the same as this x. It's just this x is a vector, so it's a 3D position. X comma direction. If you get to mapping to sigma and color, so this is the function that NeRF is fitting. So if you take, this is the NeRF model, you have this input 3D point, then viewing direction. If you give these two inputs, you get outputs density and color. This is the basic input output. Any questions in this?
I didn't get what does density represent?
Density is so here I just gave you an example with clouds. So if you take a 3D scene of a cloud, and this part of the cloud is dense, that means like a lot of gases or a lot of steam, moisture is there. We can think of it as a dense region. Then this region will have high density, and if this part of the cloud is light, then that will have like low density.
Okay.
Just we will like it will be clear when we do rendering. Actually,
Okay,
why
okay,
we
okay.
need the density. So if you take a glass, if you take a block of glass, let's say this is a block of glass, like a rose colored glass, and if you take a like a block of, I don't know, plastic, then even though they are the same color, let's say this is the same color, same rose color, this glass, the points inside this glass block will have low density than the points on this plastic block, because
Yeah. I think it's
uh,
the same we used to have in physics, like mass upon volume for the volume density.
so this is not exactly like a
Exactly.
mass density, like this is that is a density of mass over volume, but this is a like a density that we are training. So we will train the neural network model. So this is a like a density in the sense of absorption emission. So
Okay.
so when we come to rendering part, this high dense points will uh, when you render, it will emit a lot of its own color, and also it will absorb a lot of we will come to that point later. So it will emit a lot of, like, let's say you have a wait. Let's say you have a rose glass block here. Okay. Oops, sorry. You have a rose glass block here, and you have a, let's say, blue plastic block here. Okay. A rose glass and blue plastic. Okay. Then let's say you are looking at this scene from here. if you look at the scene from here, you are seeing in this direction, right? So you will see some, when you take a picture from here, in the picture, you will see some rose color, and also you will see some blue color in the background. Do you agree?
Yeah.
Do you agree? Because there's a rose glass and also blue plastic. So if you look at it from this side, you will see some rose color, and also in the background you will see some blue color. But let's imagine you take a picture or you look at it from this side. What you will see?
Yeah, more like the blue glass, and in the background will be seeing the rose glass, right?
Yeah. So in the image you will just see a blue block. It will just be blue because
Oh,
you
So
like
it's
blue.
like opacity value, right?
Yes,
How,
opacity, exactly. Yeah,
yeah.
opaque. Yeah, opaque is a very good
oh, got it.
analogy. Yes,
Okay, just the plastic, so you won't use it. Okay,
yes,
okay.
yes, yes. So
Mm,
thanks, Sarad, for that word. So
Okay,
opacity is
okay. Thank you.
is the right aspect to look at it. So
Mhm.
mm,
opaque material will have a high density, and less opaque, like transparent material, will have less density. Yeah, so
mm.
that simplifies my job. So we can move on, right?
Yeah, yeah,
Yeah.
yeah.
Okay.
Thank you.
So the NeRF is implemented as a branched multi-layer perceptron. Okay, so if you look at this diagram on the right, you have this XYZ 3D coordinate input. Then you pass it through a MLP. This is like the main chunk of the MLP. So you have the like many layers are here, like I think 8 layers of multi-layer perceptron. Then after passing this 3D point through the 8-layer MLP, it gives out sigma. For this particular point, it gives out the density and also a latent space vector. So this vector doesn't have any semantic meaning, but it's just an output vector. Then what you have is you have like a head here. I think just one layer head, which is called color head. And then what you do is you take the angles, and then you take this vector from this main chunk of the multilayer perceptron. You pass these two through the color head, and then you get RGB values. Okay, this is the overall architecture of how they have implemented it. And in practice, it is implemented as MLP with a branch. Density sigma depends on X, color C depends on X and D. Okay, so now I have a question. I want someone who like I shared this slide deck earlier in the chat, so someone who hasn't seen the answer can try to answer this. Why the authors have chosen that? Why density depends only on 3D location and color depends on location and viewing direction? So this density sigma, we are predicting it as a function of just X, but the color we are predicting is as a function of X and D. Anyone wants to volunteer to answer why that is the case? Who has not seen the answer before?
So I'm just thinking, okay, so uh density depends on the X. So X is the space from where you're looking at, or X is the
It's
space of the
a
object?
point in 3D, point in the space that we are interested
Yeah,
in.
I think X is the
Yeah, so
point
the
at which
density,
you're estimating the density, right? So irrespective of where you view it from, the
Hmm.
density would still be the same, right?
Hmm.
At a fixed location. But like just based on the example you gave earlier with the rose-colored glass and the
Yeah,
plastic,
yeah,
depending on where you view it from, the color that is going to appear is going to be different, right?
yeah.
Or
Yes, but the density is a function of each point in space. So whether we are looking at it from here, so you are on the right track. But one thing is that density is a property of each point in the 3D space. So let's imagine this point has a value sigma 1. Then whether we look at it from this side or this side, this is going to have the same sigma value. Like
Right.
there'll be sigma 1, there'll be sigma 2 here. Sigma 1 will be less than sigma 2. But the density is a function of 3D space. So this point will have this sigma. It doesn't depend on the viewing angle. So sorry, I interrupted. Like, go ahead and finish your answer if you.
No, yeah, that's exactly what I was thinking, that irrespective of where you view it from,
Yeah.
since it is a property of the space itself, it would be fixed. But with the, I feel like with the color, it's going to vary dependent on where you're viewing it from, because it's a property of not just the fixed point, but I feel also what's around it.
Okay, so color, like I think you are on the right path, but I think you're confused between the color on a 2D. Let's imagine this is an image, okay? Image, and each point, each pixel will have a color, but the color that I was talking about previously was color, like it's not actually color, it's like the emittance, color emitted from 3D point. So let's take this point has sigma 1, this point will have a C1 color emitted. This point will have another C2 emitted. This point will have another C3. So each point in space will have different color emissions. So whether we are looking at this or this, like obviously the pixel color, like in this specific example, the same pixel here will have a combination of pink and blue. Here it will have just blue because this will just block everything. But then that color doesn't change the fact that in 3D space this point also has a color. So there are two notions of colors here. One is the final pixel color and also the color of the light that is emitted from each point in the 3D space.
I see. Okay. Yeah, I think I was a little confused.
What the claim is that this color, it will obviously change. If you look at it from here or here, it will obviously change. The claim is that not the change in this color, but the change in this color itself in the 3D space. If you look at it here, the color emission from this point in 3D space itself will change. So you see, you will get P1 dash if you look at it from here. That's the claim.
I think it's because the angle would also be like, so it will give you a different part of the scene from where the light is emitting from, the interactions between them. So the final thing that you should see will depend on the angle also, because of the interactions between the different radiance coming out of each space point.
Yeah, I think that's closest to the answer I was expecting. So yeah, that's good. So this is exactly right. So this the why they have made C as a function of both point and direction is to capture the light transport properties. So this light transport properties is also like a topic in this graphics and rendering, which I am not an expert, but yeah, so in order to capture those properties well, you need to depend on D as well, because the simplest explanation would be uh, let's take a surface. Okay, let's take I don't know, like if you see a glass table in your house, like a quartz table, like a marble table, take a point on the surface. That's a point in the 3D space. And then if you think the sun is here in this angle, and uh, this is reflecting light like this. Like if the surface is smooth, it will reflect light like this. So if you look at this point from here, you will see a bright spot here, like a yellow. Like let's imagine this is a gray marble table. If you look at it from here, it will not be gray at all. Like you can imagine there will be a reflection here, which is like yellow.
Yeah.
But if you look at it from, let's say, this angle, if you look at the same point, you will see gray color. Do you agree or disagree? In your in the physical world, like let's say there is a light source like a sun here, and if you look at a shiny surface from a specific angle, you get very shiny reflections of the light source like the sun. But the actual surface color of this would be gray. But then if you look at it from a different angle, the same point in the 3D space would appear gray. Do you agree or disagree?
Yeah, that happens. I agree.
Yeah. So
Yes.
that's why, like,
Yeah,
sorry?
something like this. If you see in my
Yeah, exactly. So we want to capture this kind of thing. So we want to be able to render from this angle, and also we want to be able to render from this angle. So if you just say sigma is a parameter of x and color is also a parameter of x, you can try to train a neural network, but then this point will always have the same color. Then if you render it from here, or if you render it from here, this will appear gray. You will miss the light transport property that, okay, there's a light source here, it is hitting this point here, and it is reflecting. So
Yeah, agree.
you will miss that. So there is a concept of non-Lambertian surfaces. So Lambertian surfaces are surfaces where they diffuse light perfectly. So Lambertian surface, like you can, if you take a matte painted car, let's say matte blue, no matter what angle you look at it from, it will be matte blue because the surface will spread light evenly. You will not have a reflection, but non-Lambertian surfaces are very common in 3D environment, which are shiny. So they will reflect light in a uniform manner. So in order to capture that, if you define C as a function of both x and d, it can capture non-Lambertian surface as well as Lambertian surface. Like the neural network can learn to ignore viewing direction and just depend on x in certain regions. So you capture that complexity. Agree?
agreed.
Yeah.
Okay.
Okay.
So my next question is, why don't we just take sigma also as a function of x and d? Or is there any scenarios that you can think of where this density is a function of viewing direction as well, d as well? Is there any scenario that you can think of, anything in the real world that you can think of? Where I have given you an example where this C color is a function of both location and also viewing angle. Can you give me an example where is there scenarios where sigma is also opacity is also a function of D, or if it is so, give me an example of such a scenario. I'll give you maybe 1 minute and then move forward in the interest of time.
Yeah, maybe if we think about uh, so if there are let's say you are looking through a glass from here, so so from here it would seem like that this is opaque, so the density is less and everything. But if you keep on moving this way, there will be a critical angle at which it would completely reflect, and the density should be higher at this point.
Yeah. That's very clever. That's one scenario. Yes, you are absolutely right. So there could be a glass block, and then if you look at it here, then you will be able to see something in the background. But then if you look at it from here, like even if there is something here, you may not be able to see it because like you will see some reflection of some object here. So you are absolutely right. So this is one scenario. The other scenario, an easy scenario would be Polaroid glass.
Yeah,
So if you
exactly.
have a Polaroid glass, if you look at it from this angle, it is perfect, like it is very transparent. But if you look at it from the another angle, it is opaque. Like you won't be able to see things on this side. So polarization blocks light in certain angles. That means this opaqueness or transparency is also a function of where you look at it. Like you wear polarized glasses, sunglasses, then like you are driving and you are able to see the road and the cars ahead of you. But the sun on this side, the polarized glass will block that light from reaching your eye. So that's so there are in real life there are scenarios where this density is also a function of D, but those are very rare. Like authors have ignored this because
It's very rare.
most scenarios in life can be captured like this, and also it is I think for training purposes, like for ease of representation, they have gone. So volume density predicted as a function of location encourages multi-view consistency. Only a few material have density, opacity that depends on viewing direction, polarized glasses, etc. As we saw, RGB is predicted as a function of location and direction, captures light transport properties, reflectance, reflections, and stuff. So, any questions?
No.
Okay, so I'll go to the final. Like I have so this is so NeRF model where like a revisit is just a multi-layer perceptron, fully connected feed-forward network, 3D coordinate process through 8 layers with ReLU activation. So the main chunk of the network is just 8 layers with ReLU, and outputs density and a 356 dimensional feature vector. So the main 8-layer MLP outputs this density and also this feature vector. It's a 256 dimensional feature vector. Feature vector and viewing direction processed through a single layer, like a color head, to output RGB values. So that's what we saw before. You take this 256 dimensional feature vector and also this viewing direction. I think they are just converting it into some vector form of representation and then feeding it through a layer one head and then getting RGB values. So this is the basic NeRF model. Any questions up to this point? Okay, so we have covered 3D shape representation, novel view synthesis, and also NeRF model. But then we haven't we have seen how NeRF represents 3D shape, but then we haven't actually talked about how we can go from NeRF to like a rendered image. So for that, like we need to learn rendering with radiance field. So as I told, like the concept of radiance field existed long before NeRF. So the authors borrowed the theory from rendering of radiance field to do rendering with their model as well after training NeRF. And then we will at the end we will also look at how they train the NeRF. So before moving forward, it's 12. Do you want to stop here and then do another session for rendering and stuff, or do you want me to continue? Because it is a little bit math.
Yeah, it's up to you. I think it's up to you if you want to go ahead and everybody is okay with that because
Okay.
yeah, I am okay with that. I'm enjoying this.
What about Uday, Aditi, Daya?
Go ahead because I think the flow is yeah. Go ahead.
Yeah,
You said go ahead, right?
yeah, good with anything. Yeah.
What about Uday said thumbs up? So I think I will go ahead, and if you feel like this is brain freeze or some overload, just let me know. We can do another session. So okay, so we will first look at rendering just one pixel. So we will look at a ray through a radiance field and see how we render just one pixel. Let's imagine this cloudy radiance field, and then you have picked an origin O, and then you are looking at this. So okay, so I think I have to. So you must have taken this image processing or computer vision class where you have a camera origin, and then you have the actual image plane in front of the camera, then you have the 3D scene. Then from the origin, you have these rays that are going through. Then on the image plane, the pixel values that you will get are like whatever in the 3D scene, that is the lights that are traveling towards the origin. So you try to use some lens to focus on this image plane. So this is kind of like, I don't know if I don't remember like these things. These are very fundamental, these camera things. So do you remember this learning this kind of thing? So there will be I don't know what like there will be a principal line here. Then this point is called something. There are some theory like this. Do you remember those kind of things?
Yeah.
Yeah. So there's a concept of origin, and also there will be an image plane, and then there will be scene, and then there will be rays going through here and there. So you can think of it in a similar manner. So there is an origin, then there is a cloudy 3D space. But it can represent anything, and then if you fix a direction, like let's there's an image plane here, and you want to render this pixel, then then you draw a line. Okay, now imagine this is the pixel that you want to render. You draw a line from origin to that pixel, and then that's a fixed angle, right? So you can change the location along this line, and then the combination of all these lights emanating from different parts will be the value of this pixel. Do you get the basic idea here? So here we are defining this line in a vector linear vector equation. So this RT is this representation of this line. So any point along this can be parameterized by T, and then this RT will have points along this line. So it starts from when T is 0, this is just origin O, and then you have a unit vector in the direction that we are looking at, that is called D, unit vector. Then you can scale this unit vector and add it to this origin vector, and then you can get any point along this line. Do you agree or disagree? That is some vector equation, right? Okay.
Can you
So
explain T? What is T for?
yeah, so you let's say you have a origin vector here, then you have a unit vector D
Mhm.
in some direction. Some direction you have a unit vector D. Then consider the equation O plus TD, where T is T belongs to some I don't know near boundary and far boundary. Just ignore this for now. So if you take this and you take T as 1, then it will be this point. If you set T as 2, it will be this point. If you take T as 3, it
Okay.
will be this point. So you can represent any line along, any point along this line with this equation just by varying T.
Mhm.
T is like a parameter that you can change and represent any point along this line.
Yeah.
And
Okay.
also, we just take a slice in the space called, this is the Tn, this is the Tf. These are the boundary, and we are interested in points between these lines, and we can ignore points here and here. So that is
Is
the
D a unit vector or it varies?
D is a unit vector.
Okay.
It's a ray direction. I would imagine it's a unit vector, and these are near and far bound. So just a diagram of parameterization. So this is the origin. This is the direction. We can look at direction as a unit vector, and then there are two bounds like near boundary and far boundary, and we are interested in points between this.
Yeah, got it.
Okay, so this is parameterization of a ray. and then the volumetric rendering equation. So NeRF uses standard emission absorption volume rendering. So in the radiance field theory, they had some, like, I didn't also learn about radiance field theory, but then when I looked at NeRF, they said they are using this emission absorption volume rendering equation from radiance field. So it is given by this, which is CR is the, if you take a, if you go back to this, so if you take this point in the image plane, that color of that point will be given by CR. Color of this is the color of the point in the image plane, not the 3D plane. So here this CR is the color of the pixel in the 2D plane, and this CR comma D is the color of the point in the 3D space. And you can take the color of the pixel as the integration from, you integrate from here to here, you integrate over this region of interest. You have three quantities here. One is the color of each point along that ray, and then you have the density of each point along. You have a, let's say you have a ray like this, you have within these bounds, each point will have a color and then opaqueness or density, right? So this is nothing but for each point you multiply C and sigma, so that it kind of gives you the strength of emission. So we have seen in this example, like when you here this C1 is rose and sigma 1 is, we saw this sigma 1 is lower than sigma 2. So the strength of emission of light at this point will be low compared to the strength of emission of light at this point, because this point has a high opacity. So the final image will have more of, more like, if you compare these 2 points, this point will have a higher strength than this point. So you multiply C sigma, it will give you kind of like a strength of emission at that point, strength of the color at that point. So this multiplication gives you that, and these quantities we have seen before, but this T is called transmittance. I think you must have seen this in electricity, and I think electrical theory also has this transmittance. This is the probability that the ray has not been absorbed before T. Let's say, if you go back to this same example, so if you look at it from here, and if you come to this point, and then you consider the transmittance, so within this region, the transmittance is high, because like there is nothing in this area, so you can actually see this pixel. And once you go into this region, the transmittance is a bit low, because like some opaqueness has to be taken into account, but then still you will be able to see this region. Once you come here, like you will be able to see this pixel, because even after crossing this part, you still have some transmittance. But once you come here, the transmittance practically becomes 0, because this is like a solid plastic block, right? So so that is a notion, but this is for viewing from this direction. But if you view it from this direction, the transmittance will be high in this area, because there's nothing there. But once you hit this plastic block, in this entire region, the transmittance will go to 0, because it will absorb everything. Like it will not let anything pass. So that is kind of like the idea. So that is why they have this transmittance in the equation. So when you are looking at it from here, this transmittance makes sure that you integrate some amount of light that is emanating from this region and some amount of light that is emanating from this region. Transmittance makes sure that you integrate, you add both to get the final capital C color at the image plane. But when you look at it from here, the transmittance becomes 0 here. So once you do the integration, you only get the color from this part. This pixel will only get the color from this part, nothing from this part will come into play. So that is why transmittance is used to wait as you go along the ray. Do you want get the intuition?
Yeah.
Yeah. So, and also the nice thing about this is that you don't need to learn anything else. What you can do is you can we have seen that this sigma is like a opacity, right? So you can just take let's say if this point has sigma opacity, then the transmittance of this is just 1 minus sigma. Just the opposite of that is the transmittance, right? Like if there is a very solid block here, the sigma will be high, then 1 minus sigma will be close to 0. You get it, right? So we don't need to learn or parameterize this transmittance by using anything else. You can just use this the same thing density to parameterize transmittance, and this is the formula that they have used. So it's integration like from this point t near to, let's say this is the point, this is the t point that we are interested in, then you integrate this part of just the sigma, like all the densities along this region, you integrate it, you just take a negative of it and take that to the e to the power negative whatever the quantity that you got. So I think they have chosen this. I don't have a clear idea why they have done like this kind of thing, but maybe some theory behind it or some practical purposes. I don't even know how. I think
Yeah, I think transmittance depends on it's like an exponential decay.
yeah,
It's not
it
linear,
will be
so it's
something
like
like this,
exponential decay.
and it
That's
will
why
be
they
0,
have
it will be 1, and then it will be exponentially decaying once you go. So this is kind of like an equation. So the basic notion is that like you get it right. Like if you are looking at from an angle where the things in front of you have low density, then you need to go until like a very long distance to get all the information. But if you are looking at from a direction that has very high density things up front, then you just don't care about things that are behind. So to do that weighting, you use this transmittance. So here in this, I have messed up this slide, but then this is just the integration of from this point to this point. What you do is you just integrate this multiplication of these three quantities: color, density, and transmittance until that point. So transmitter until that point, it's transmittance just how much weight you are going to give to that point. Then you multiply all these three and then integrate it from this boundaries that we are interested in. We are interested in this region and the space, and then you integrate it. That will be the color of the pixel that you get in that point. So if you go back to the previous diagram, this is the ray, this is the image plane. In order to get this pixel, you just integrate color, density, and transmittance in this region, and that will be the color of this pixel. Any questions? Okay, so that is the standard emission absorption volume rendering. Now you can see what we can do with NeRF, right? So intuitively, what you can do with NeRF is you have now assume like we have a trained NeRF model that is representing the 3D volume. Then what you can do is you can pick an origin, you can pick a ray, you can just take points along this, like you can take x1, y1, z1, x1, x2, y2, z2. You can take a lot of points along this, and then you can query NeRF. NeRF will give sigma and RGB values. Then you can get all these values and do an integration along this line, get this pixel. Then now you can pick another line, another pixel, then query points along this, and then get the value from NeRF and integrate it, get this pixel value. Do you get the basic idea? So that's what they do. So this is a continuous equation, but in practice, like since we have, like, even though NeRF represents continuously, like just querying for all the points along this line is a very expensive operation. Like you cannot continuously query, right? Even though the model is continuous, you cannot continuously query because that will take a long time to like do all this. So what they do is they discretize this equation. So let's say this is the cloudy region. These are the boundaries we are interested in. Instead of looking at all the points, we are just going to look at a few points. That is what this is. So instead of having a continuous integration, you just discretize it. You pick a set of t parameters, t1 to tn, and the delta will be the difference between this. Then you evaluate the MLP, the trained NeRF model at each point that you have picked along this line. Each discrete point, you get the information. So for each ith location, you query the model using the X and D, and then you get Ci and sigma I. Then define the per sample opacity. So using the constant density, like these are some like theory, because previously in this equation, each point in the space had some density. So we just integrated that function. But then once you discretize it, so this you have discretized. So this point will have some sigma. This point sigma 1, this point will have some sigma 2, but then you cannot directly like add the C1 sigma 1 plus C2 sigma 2. You cannot do that because there is some space in between, right? So let's say this is delta x, then you need to do some kind of sigma times delta x to actually get the density of this discrete interval, right? You get it, right? So for that, like you cannot just do sigma times delta x. They have a formula for this per sample alpha opacity. So what they do is they define an alpha I equals 1 minus x e to the power negative sigma I delta I. So delta I is the width of the sample, and then you multiply it by this, and you take exponent of it, and then you do 1 minus. Then I think it's something like you go from 0 to, then you asymptote to 1. Then that will be your alpha. So if you take a small width, then you get some small value. But if you take a very large, let's say you take a very large like you take a point here, you take a point here, there's a big difference, but then you don't want that opacity to blow up, so you just limit it to 1. So even if you take a large delta, you still get something close to 1. So that's why I think they have used this formula. It's any questions in this? Like these are some mechanical things in the. So now you have a notion of what is the opacity per delta, and then you can do transmittance in the same manner. We have seen if per sample, if alpha is the opacity, then per sample the transmittance is 1 minus alpha. That is the same, because you just opposite of the opacity is transmittance. Then what you do is you just multiply. Like let's say you have a line segment here, you are here, but then this is your starting boundary, this is your ending boundary, you are here, and you have, let's say, 5 intervals here. What you do is you take 1 minus alpha 1, 1 minus alpha 2, 1 minus alpha 2, and you just multiply all of this, and then that will be your transmittance at this t point. That is what is given by this equation. Any questions?
Yeah, just one thing. I'm just thinking, so if you just directly substitute alpha I inside the TI's equation, Wouldn't that just cancel out 1 minus 1 and you're left with exponent term?
Yes, yes, yes. I think you're right. You can just substitute this into this, and then 1 minus. It will be just a multiplication of this exponent terms. You're right. Yeah. If you just submit it, it will be substitute it. It will be just a multiplication of these exponential terms. You're right.
Okay. Okay.
So yes. So this is a way of discretizing the continuous integral that we saw before. So after you discretize, now we have all the tools that we need to do rendering with NeRF. So the rendered color is the weighted sum. Like you take a ray, you take C1, C2, C3 along these points along the ray, then you just take a weighted sum, and then that will be the pixel value, capital C here. So that is what is they have represented by here, and the weight is Ti alpha I. That is natural from the thing, right? So this is all, you can consider this integral also as a weighted sum of colors, where you are weighting by the density and also transmittance. So the same thing here. So the C is a weighted sum of color, and you are weighting the color by transmittance and opacity. That's natural from there. Do you get it?
Yeah.
Okay. So they also sometimes do render the depth. So I don't think we need that. So what you can do is you can take these weights, Ti alpha I, and then multiply it with, at each point you have this Ti as well, T1, T2, T3, right? We saw this R is equal to O plus TD. So this T value, you vary along this line to get each point. So you take this T value and then multiply it by the weight, and then if you get the summation, it on expectation it gives the depth. That means like if there is a scene of I don't know, a block, like I don't know, a mountain here. If you look at it from here, you take rays, and then you render this depth, then it gives you, on expectation, it gives you the distance between the image plane and the hard surface that the ray is terminating at. So it requires some imagination, but then like I don't think we need to go into that. You just understand the rendering of color, but you can render the depth also, and also in expectation it will give you the distance between your, I don't know, image plane or the origin and the hard surface that the light is terminating at, something like that. So this is another way to look at what we are doing. You take a ray, you take samples x1, x2, x3, and xn, and then from here to here you use a NeRF model. You input this information into NeRF, you get density, and then you calculate alpha, and then you calculate weights, and you end up with a set of weights. Then each points, in addition to the density, you will also get C1, C2, then you multiply these two, and then sum and get the final pixel color. Then you do that for all the, so this is this rendering procedure I have explained for just one pixel. Then to get an image, you have to do this for all the rays that are going through that image plane. You have to do it for everything, and then finally you will get a image. That is the rendering process. Any questions on rendering?
So this way we have resolution invariance, right? Like
No.
we can render for any resolution.
Yes,
of
correct. Yes. So we can pick and choose the directional variance that, like we can vary the direction by certain steps and get one resolution. We can vary the direction by even finer steps and get a different resolution. And hopefully our neural network model will learn no matter how small the distance changes, the neural network will give some information. Then after rendering, hopefully we will end up with a higher resolution image. So as you rightly pointed out, there's no limitation on the resolution. There's continuous variation. So here in the discretization, what we have done is we have discretized per pixel we have discretized the number of samples, but we have not actually discretized the pixels. So we are free to change, like we choose if there is camera O here, we let's say we only do 5 different directions, then we get 5 pixels. If you do 50,000 directions, then you get 50,000 pixels. So we are free to change that and get as good resolution as we want.
Yeah.
Okay. Any other questions? Anybody else? All clear?
Yep.
Okay. So, okay. I'll little bit rush through this because I think we are like 12:20. So a little bit rush through this. So we'll look at how we train NeRF. So I think we have already seen how to do it. You take a 3D object, then you take multiple images. Let's say here this is a backhoe. You take multiple images of the backhoe. Then what you do is you initialize this model to some like you initialize the multilayer perceptron to some value, but then you pick a viewing direction, then you query XYZ along this, you do the rendering, and then you try to reconstruct this image. Then compare these two images and then back propagate the losses through this, and then then you do this for multiple images. So this we have done for one image, then you take another side, and then you vary this XYZ, then give different inputs to this multilayer perceptron, get the output, integrate it, try to render this image, then compare these two images, try to back propagate the losses, try to train the weight. So that is what and here this is just a visual representation of, let's say, this is the distance, and then if the opacity is high in some region, the final color will have more of that high opacity color. This we have seen, right? Like here it is yellow, but here it's brown. But since sigma is higher here, the final will be more brown. Then if you look at here it's brown, here it's yellow, but it's a bimodal sigma. Then once you integrate along this, you get some orange kind of thing, combination of this and this peaks. Just some visual representation. So this is the pipeline. So training objective is photometric loss. Photometric loss is nothing but pixel-wise difference of RGB values. So given post images, non-camera intrinsic and extrinsic, we sample many rays and minimize the mean square error between the rendered and the ground truth pixels. So here we have seen how we can render this CR. So if you go back to this, we have a formulation to render for each pixel. We know how to render the final image color. Then you do that, and then if you render from a non direction, so you had during training you had to render from you had to render from the directions where you have data images. So if you have an image of the backhoe from this direction, you try to render from that direction and then compare these two images. So here you have the ground truth C star. Then for each pixel in the image, you take the L2 difference, and then the total difference between two images will be the photometric loss. This is a simple loss objective. You get it, right?
Yeah.
Okay, then I think beyond this point, I think I will discuss some stuff. So those are not really essential theory. I think we have covered all the essential theory until this. The rest are just whatever they have done to empirically improve the performance. So if you ask me why they have done it, I have no concrete answer why they have done it, no physical or no meaning, but they have chosen to do it because it improves the empirical performance. So in the NeRF paper, authors are using two networks, one coarse and one fine. So the total loss would be the loss of the coarse network and the total loss of the fine network. Just the addition of that will be the loss. And there are some hierarchical sampling. I think I can stop here. Like these are not really important to the theory. These are just some mechanical things that they have done to improve the performance.
Mhm. Yeah, yeah,
How
I
they
think.
can do hierarchical sampling and then coarse pass, fine pass. Those things I think we can skip. This is not. If you are interested, ask me. Otherwise, like I'll stop here.
Yeah, I think we can stop here
Yeah,
because
yeah.
I
I'll
think.
just skip to the training loop. So this is the training loop. You pick an image, sample a bunch of pixels, convert pixels to rays using camera intrinsics and extrinsics. You know the direction and the ray angle. Then for each ray, sample points. Along that, you sample the points. You run MLP, get sigma and C. You compute alpha I, T I, W I. Render the. You have to do it twice because there are two networks, but we will skip that. You render C. Then after you have completed for all the rays, now you have the entire image. Then compute the loss versus ground truth and back propagate. That is the pipeline. That is the training loop. And then that brings us to the end. And this is nothing but the link to their page where you see these impressive visuals.
Mhm. So I have a question so in training, it is generally better to have very high resolution images, right? Because your loss is being calculated on the original image that you had, right? So it's good to have high resolution images, or is it like you can have low resolution images also, and then it might also work?
I would think that having higher resolution images and having more images both would help increase the accuracy of nerve. Like as you rightly pointed out, you have a higher resolution image, then you have more information. And if you have multiple, like let's say you have a drum set and you take 100 pictures and you train a nerve. You have a drum set, you take 1,000 pictures and train a nerve. Obviously the one trained with 1,000 images would be better. And also if you take 100 images of a drum set, let's say 1024 by 768, and you train a nerve, and then you take 4K pixels of the same, but then 100 number of images, you train a nerve. Obviously, as you rightly pointed out, in my understanding, the nerve will perform better. But in the training loop, what they are doing is they uh, oops, where is that? Okay, I think it stopped. Okay. Yeah, so you pick an image and you sample a bunch of pixels. So you take a origin, you take an image, then you have this 3D. Then you don't do rendering for everything. You are randomly picking some pixels, and then you are doing this ray matching and alpha blend. So so you are computing alpha, and then you are doing some blending, right? So in graphics, this is called alpha blending. That is used for game developments and stuff as well. So I'm just giving you that term. So this is very like the authors have taken this idea from alpha blending. So yeah, so you don't do it for all the whether it's 1024 by 768 or 4K images. You don't do it for every single point, but then you are doing this repeatedly to train, right? So obviously having a 4K would have a higher like a higher number of samples from which you can sample a batch. So obviously that would lead to a better, like that would lead to some good performance if my intuition is right. Like that's my idea.
Hmm. And this hierarchical resampling steps, is it also related to that in some way?
No, hierarchical sampling is related to how you sample along the ray. So we have seen that like you take a ray, you have a T near and T far. These are the boundaries. You look it from here. You are integrating or summing along this region, right? So what you do is first you take, let's say, coarse samples, like let's say 5 points from here, and then you calculate the color of the output. Then what you do is once you sample points here, then you get sigma 1, sigma 2, sigma 3, sigma 4, right? Then you look at what points along this have higher sigma. Let's say if you consider this as a density function, let's say if density is increasing like this is the value of sigma. Sigma 1 is high, sigma 2 is high, sigma 3 is low, sigma 4 is low. Then after you have done this first pass, you do fine pass with the fine network where you sample lot of points in this region, but then sample few points in this region because you know this region is very dense and this region is very light. So that is the fine sampling. So coarse and fine it's along each ray,
Okay.
not along the pixels on the image. The pixels along the image is fixed in this first step itself. After that, you do this coarse and fine for each ray.
Okay. Makes sense.
Yeah. Any other questions?
No, I think it was a great presentation. Just thinking everything in. This was a relatively new topic for me, so learned a lot. So thank you for the presentation, everyone.
Yeah. Thanks.